sometimes ever. Is mine. I don't know.
Okay, so let me just quickly kind of summarize here that one of the last things we did last week was we looked at the high frequency impedance of a wire, solid, round, like copper wire, radius A, length L. And we had derived a formula for the input impedance, which is R plus JX. And we noticed that R is equal to X, and they're both equal to what's called the surface resistance of the metal. Now remember, surface resistance has nothing to do with dimensions. It's just a property of the metal and the frequency. But then a geometry factor, which is the important thing, length over circumference. So that's kind of the takeaway message. The resistance, which is also equal to the reactance, is the surface resistance times length over circumference. So now we derived it for this round wire, but if you understand that principle, resistance times length over circumference, my claim is we can apply this to almost any shaped wire. It doesn't have to be round circular wire. Okay, and ultimately what we do is apply it to the coax. Okay, and again, this is the equivalent circuit of a piece of wire at high frequency. Now let me remind you that the surface resistance is given by 1 over the conductivity of the metal times the skin depth, and you can remember it like that. Or if you want to plug in the formula for the skin depth, square root of 2 over omega mu sigma, you can get this formula for the surface resistance. Okay. This one kind of makes it more explicit that the surface resistance gets small if the conductivity gets high. It's 0 for a perfect conducting wire, but it also gets high as the square root of frequency. So again, wires at high frequency, like microwave frequencies, have much higher resistance than like a DC current flowing through a wire. And I showed you that table last time. Okay. Now with that in mind, let's go to the coax and apply our knowledge to the coax. There's a cross-sectional view of the coax. So notice inner radius A for the inner conductor, which is a solid wire. And then we have radii B and C. So the thickness of the outer conductor, the shield, is C minus B. Okay. The gray region is the Teflon or the insulating material. And the thick blue shaded region is the region where we expect strong currents to flow on the coax. Because remember, let me remind you that most of the field, most of the Poynting vector is in the Teflon region, but then the fields are penetrating from that region into the inner conductor and outward into the outer conductor. But remember, they're decaying exponentially, so they don't get very far, right? After a few skin depths, they're almost negligible in amplitude. So that thick blue region that's highlighted is not very thick, maybe a few microns. Now, anyway, apply the same formula we just learned for a wire, but I'm going to apply it twice for the interconducting wire and for the outer conducting shield, as we call it. Okay, keeping in mind that the radius of the current on the interconductor is A, and you see this blue region here. So the radius where it's flowing on the outer conductor is essentially B, not C, right? B, because it's penetrating in from the inner region here, right? So radius B for that region. So the total resistance, therefore, of the interconductor, the wire, is surface resistance, we'll say, of the A conductor. The A reminds us that it's for the A conductor because they may be made out of different metals, A and B. Length, whatever the length of the coax is in the Z direction. Now, of course, if you're trying to solve for resistance per unit length, then you'll divide out the L, right? But right now I left it in there because this will be the total resistance in ohms for a length L. And then divide by the circumference, which is, of course, 2 pi times A. Now, for the outer conductor, we do the same thing. It's the same formula, but I'll put a B there because it's going to be a different metal, different surface resistance, same length L in the Z direction, and circumference, remember, B, not C, but B. Okay? So it's the inner radius of the outer conductor that's important. All right? And then the total resistance just comes from adding the two together. Now, notice that the currents are flowing in equal and opposite direction on the two conductors. Okay, so these two resistances on the A and the B conductors are added in series. It's not two resistors in parallel. If you have two like wires and the current's flowing in the same direction in each one, you would say that the current is splitting between them and the two are in parallel, right? Like two resistors running side by side, that's two resistors in parallel, right? But if I have like a loop where I have a resistor going this way, current's going this way, coming around, coming back on this resistor, those are in series, right? So it's a series effect because the current's going like this in opposite directions, forming a loop in the whole system, not in parallel. So we add the two together, and again, divide out the L if you want resistance per unit length, which is what we, that's what the R parameter means in RLGC, right? Resistance per unit length. So we divide out the L. So there it is. That's what we call R for the coax, resistance per meter of the coax transmission line. Okay. And again, although we've seen it before, here it is. The surface resistance of the A metal, the B metal, and notice they could have different conductivities. They could have different skin depths. So, this formula has A everywhere, and this one has B everywhere. Of course, it's the same frequency, obviously. Okay. So does that make sense? So that's how. So finally, we see where it comes from. So that's the resistance per unit length of the practical coax cable. And let me just remind you where it fits in the overall scheme of things. So for the coax, here's the four fundamental parameters, RLGC, and this one I've been highlighting in red here. We finally have gotten to it. So now you see where the derivation comes from, and now you see where this formula comes from here. So resistance per unit length of the coax. And of course, as you know, what you would do with all four of these is plug it back into the formula for gamma, and then separate out the real and imaginary parts. And for example, the real part is called alpha, meters per meter, and of course, multiply by 8.686 to convert that to dB per meter, as you know, right? Okay. And one more reminder. I talked about this last time, but one more reminder. This is the G formula in terms of the loss tangent of the dielectric. An equivalent formula, as I talked about last time, is to say that we can use what's called the effective conductivity of the dielectric, which is related to the loss tangent of the dielectric by this formula here. So if you have a problem, and the problem gives you loss tangent of the Teflon, or it gives you the equivalent effective conductivity of the Teflon, be prepared for either case, right? You know how to convert them back and forth with this simple formula right here. Okay. So that's the G of the transmission line. And remember, G counts for loss of the dielectric. R, of course, counts for the conductivity, the loss of the metal. Okay. Here is one practical transmission line. Of course, you've done a similar one in the homework. But here's something called the RG59 coax, a very common coax, actually taken from Wikipedia. Okay. And here's a little mini table, similar to ones I've showed you before, where I'm giving you dB per meter of this coax. And you can see that the main message is it increases as you go up in frequency. Now, if you go back to these formulas, okay, let me remind you of two things. First of all, as we just said, the resistance has surface resistance in it. And if you look at the formula for surface resistance, here it is again, for the A or the B conductor, you see square root of frequency. Okay, so the surface resistance increases as the square root of frequency, and that makes R increase like the square root of frequency. So because of conductor loss, the coax gets lossier and lossier at high frequency. What about G? Okay, now for many practical dielectrics like Teflon and polyethylene, tan delta is more or less constant with frequency, not exactly, but more or less. Like, for example, Teflon, through a wide range of frequency, even through microwave frequencies, the tan delta is typically 10 to the minus 3 for Teflon, almost a fixed number. But then look here, omega C, right? Now, C doesn't depend on frequency, neither does L, but you see the omega there, right? So G, in some sense, is even worse. R is proportional to the square root of frequency. G is proportional to frequency. So for both reasons, the coax is getting lossier and lossier to go up to high frequency. So you wouldn't worry about this loss too much at 1 megahertz. But at microwave frequencies, you see you're getting like several dB per meter, maybe a couple dB per meter. Okay, so it can be quite lossy. Okay, by the way, the RG59, as you can see, is a TV coax because the Z0 is 75 ohms, not 50 ohms, right? The microwave world uses 50, but the TV world uses 75, right? Okay. And now we haven't talked about fiber optic yet. We will a little bit later, but I just want to compare one thing. Here's that same table again for the RG59 coax. Here's some pretty pictures of a fiber optic cable, and we'll talk about it more later. But I just want to point out one thing, that that the loss in a fiber optic cable can be much less. We'll talk about this later. There's two types of fiber optic cable: the single mode and the multi-mode. The single mode is the highest quality. And I highlighted this in red because, see, this table is dB per meter for the coax. These are for the fiber optic cable, and they're dB per kilometer. Okay. Pardon?
So it's that.
Oh, yeah, absolutely. I mean, 3 dB per kilometer. So that's 1,000 times lower than like the coax at 20 gigahertz. And then look at the single mode, 0.3 dB per kilometer, right? So really, really low loss. And that's why for very long distances, of course, people are going to prefer fiber optic over coax. Coax is wonderful for going across rooms and across a building or something like that in your lab, right? But you're not going to use it to go across the city, right? But fiber optic is going to be used for that. Okay. And of course, as we know, as I already talked about, for extreme distances, you'd probably want to use wireless, right? Right. Okay. All right. Well, as usual, is appendix summarizing the most important formulas. But other than that, that's pretty much it. Okay. So let me close it down here. Any questions on any of that? Okay. All right. So let's go ahead and turn this into a review session here. And again, we can do that as long as you want. If you get tired of it and you run out of questions, we'll just pick back up with note 17, right? So the floor is open to you. Anything is fair game, questions about homework, old exams, the notes, anything you want to talk about. Got a question? Go ahead. Okay, sorry, you want to come by later or something? Okay. Anything else? Yeah, I'll give you time. You don't have to rush or anything, but is that the homework pile there? Is that the homework pile? Okay, has it gone around? Oh, okay, what's that? Okay. Please go ahead. No, didn't bring any more, but if you want to look at an old exam, I have with me, so you can pull out any one you want. Yeah, go ahead. Fall 2018 exam. Sure.
Yeah, right. I hope.
Okay, I'm sorry, which problem did you say? Problem 1?
Yep.
Okay. Part B. Okay, and here's the solutions here. If you can read that, okay. Now, by the way, let me remind you that if you look at the old exams, some of them have formula sheets included, but as I said on Blackboard, yours will not. So if you want to take that formula sheet with you to exam, that's fine, but make sure you print it yourself and bring it, okay? All right. So this one right here?
Yes.
Now, can you read that? Is that big enough to read? Let me see if I can make that bigger. All right, and you're mainly interested in part B, you said? Okay, at the very end, are you talking about this equation here? Well, so it's from Faraday's law. So curl of E is minus J omega mu H, right? So we took the curl of E and we plugged it into that equation. Did you want to see it? You'll see it in more detail? Okay, okay.
It's more of just like, so this is our final answer. We get what I have. or the term that I have
Mhm.
before you get to the final answer.
Mhm.
How did you jump from this to this final answer in simplification?
Okay, now K zero is omega times the square root of mu zero epsilon zero. The omega is going to cancel, right?
Mhm.
Okay, and then eta is the square root of mu zero over epsilon zero, right? So 1 over eta, or 1 over eta zero is the square root of epsilon zero mu zero.
Would it be too much to ask you to do it on the board?
Sure. Okay, he wants me to do it on the board, so let me do it on the board here. Okay. Again, this is fall 2018 exam 1. And he's interested mainly in part B. Okay. And so if we've already done part A, then we already have the E field in the phasor domain. So I'm going to write that on the board. Okay, so in the phasor domain from part A, this is coming from part A. There it is. And now the problem is saying that it's in free space. So of course we have epsilon 0, mu 0, and K is called K0. Okay. All right. So anyway, so part B is saying find the magnetic field vector in the phasor domain. That's the goal. Okay. And so Faraday's law would be this. U would be mu 0 for in free space. So therefore, the H vector would be -1 over J omega mu 0 and the curl of the E vector. Okay. So we've got the E vector in the phasor domain from part A. So we have to plug in here and take the curl, right? Okay. Now, so the curl of E of course, we could just look this up in the notes, but anyway, there it is. The formula for curl of E. Okay. Now, notice that we only have an EZ component, right? So, which is everything in front of unit vector Z. So this is the only thing we have here, right? So curl formula is going to give unit vector X. That's so partial of EZ with respect to Y. Minus partial of EY with respect to Z. Okay, and then it's going to be minus Y hat. Cross out those guys. So partial of EZ with respect to X. Minus partial of EX with respect to Z. Okay, now stop me if I make any stupid mistakes, okay? All right, so now we only have an EZ, so we don't have any Y, and we don't have any X. So it looks like we get these two terms right here. And not only that, but this says partial of EZ with respect to X. But see, the EZ doesn't depend on X, right? So that one's gone for a different reason. So it looks like all this boils down to just unit vector X partial of EZ with respect to Y. Okay. All right. So therefore, it looks like H is equal to -1 over J omega mu 0. Unit vector X partial of EZ with respect to Y. And of course, all this here is EZ. Get a constant e to the j pi over 4. And then we take the derivative with respect to y, we'll pull down a factor of j k0. And then e to the j k0y. Okay. Now let's see if we simplify a little bit, The J's will cancel. Vector X, J pi over 4, e to the j k0y. And then we'll have a term that looks like k0 over omega mu 0. Okay, and what is that? K0 over omega mu 0 is equal to k0 is omega times the square root of mu 0 epsilon 0. A cancel omegas. So that's going to be what? The square root of epsilon 0 over mu 0, or 1 over the square root of mu 0 over epsilon 0, or 1 over eta 0, right? So therefore, this thing here can be written as simply 1 over eta 0. Right, so that's what I get. Let's see, is that what this answer has? Okay, let's see, they have a minus sign. So did I forget a minus sign somewhere? Let's see, let's check it. Oh, what happened to this minus sign?
Yeah.
Yeah. Okay. Yeah, looks right now, I think. Okay. 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 Now, of course, from our recent plane wave discussion, we know that the ratio of E to H is going to be eta, right? Now, I don't think this was supposed to be a plane wave problem, right? But it's really testing on Maxwell's equations. But we know that that's right because the H is supposed to be E over eta, right? In the amplitude. So it's totally consistent with what we learned recently about plane waves. Okay. Okay. All right. Is that good enough? Any questions on that? Let's move on. Yeah.
So if we did convert that to the N0, then will we get points taken off, or can we just leave it?
If you didn't convert to eta 0?
Yeah.
So in other words, you left it just with like this?
Yeah.
Well, let's see. Did the problem say you had to do anything like that? Let's see. I mean, it didn't say you had to, so probably you wouldn't have a point deduction for that. Okay, let's move on. Yeah. Or whoever's first, I don't know.
Can you go to the problem number 1, 1C, and 1,
2020.
Yeah.
Okay. Part C, you said?
Yeah.
So this one right here?
Yeah. I'm looking with the surface.
So you're asking about the surface S?
Yeah. That's
Okay, so you have a particular question about the surface?
yeah. This is and then I think that you have you must have narrowed out. Yeah. Right. PC.
The what, sorry?
Right, the integration.
Oh, okay, the integration, right, starting right here?
Why has it like the E part of that BP thing?
PC stands for complex power. I'm sorry, what's the question though?
So I'm asking why the areas will be like S product P and product P.
Not sure I understand the question. Are you asking about this?
How do you calculate so this area?
How do we set up this area integral?
Yeah.
Okay. Okay, so now we're integrating over the surface S, which is here. Okay. And let's just read it here. Find the time average power in watts and reactive power in VARs going downward through the surface S. So downward means going like this. So the unit normal should first of all be in the negative z hat direction, right? Okay, so that's where we got the negative z hat from. Okay. So S dot negative n hat, which is negative z hat. Okay, so that's going to be the complex power and in VARs and watts per square meter. Then integrate over the surface to get total watts and total VARs. Okay, now S dot minus z hat is the same thing as just negative S sub z. S sub z just means the z component, right? Okay, and now, so we're integrating over the surface S, this yellow surface, which is part of a coax. And of course, that's best described in cylindrical coordinates, right?
Yeah.
Okay, so definitely I suggest carrying out the calculus in cylindrical coordinates. Now, in cylindrical coordinates, we would say that rho, which is the distance, horizontal distance measured from the z-axis, that goes from here to here. So it goes from A to B. And then the angle phi in cylindrical coordinates goes around like this, counterclockwise, goes all the way around. So therefore 0 to 2 pi. Okay. So when we do the calculus, so it doesn't matter which order you put these in, as long as the order is consistent with the differentials here. But rho I put first, the inner integral going from A to B, and then phi, the angle, the outer one, going all the way from 0 to 2 pi. Now this is the differential ds in cylindrical coordinates. The differential area is rho d phi. Okay.
I don't get that. I don't understand whereas when you calculate the area,
Well, okay, so now let me remind you again that you're in cylindrical coordinates. ds is equal to rho d phi. I mean, so do you agree with that?
Yeah.
That's not what I don't see it.
Oh, okay. Well, I think you need to go back to calculus. Right. So that's just doing an area integral in cylindrical coordinates. But a really good refresher, in my opinion, is in the 3318 notes. Okay, look at what I think is called note 6, if I remember right, which is a review of coordinate systems in 3318. Really good set of notes on reviewing coordinate systems. It talks about volume integrals, surface integrals, and all 3 coordinate systems. You might want to review that.
It's a step by step the integration just for this problem.
Oh, okay. Yeah, actually carry out the integration?
Yeah.
Okay, sure. Okay. Now, this is the S right here. Are you okay with that?
Yeah.
Okay, now this is the formula after doing the dot product, right? So now SZ, of course, remember, is everything in front of the Z hat, right? So all that, just get rid of the Z hat, and all that gets plugged right into here, right? Okay. Now I can write on the board, but let me just say it in words first, okay? Maybe that's enough to say it in words, but if you want, I can write it on the board, okay? So you're plugging all that, everything in front of the Z hat right into here and integrating. Okay, now you've got a double integral because rho is going from A to B, and phi is going from 0 to 2 pi, right? Okay, now you're doing this at one particular value of Z. Okay, let's look at the picture. So the surface S is at an altitude above the XY plane of L. So the surface S is described by Z equal L, right? So Z is not a variable of integration. Z is just going to be set equal to L, right? Okay. So see the sine KZ, cosine KZ, that got converted into sine KL, cosine KL, right?
Yeah.
Okay, you got this constant here that also just came down. Okay, you got the J that came down and 1/2 that came down. Okay, and there's a minus sign here, which cancel that minus sign.
That's really only one over rho squared. That's.
Yeah, okay, well, two things. First of all, for the phi integral, we look at the total function here and we see no phi at all, right?
Yeah.
So phi is like a constant as far as the phi integral is concerned. So it's really that integral is just 0 to 2 pi of 1. So it's just going to give 2 pi. So it simply gives a factor of 2 pi, which is right here, right?
Yeah, yeah.
Now the rho integral has a rho here from the ds, which cancels one of these rows. So you get rho over rho squared, so it's 1 over rho. And the integral of 1 over rho is log, right? So you're going to get log of b minus log of a, but from the property of log, it's the same thing, you're just saying log of quantity b over a, right? Okay, well, go ahead.
Wait, but there's a row in there, so if you were to integrate row.
Well, there's 2 rows. There's a row here from the ds formula.
Yeah.
And then the Poynting vector itself has a 1 over rho squared.
Oh, okay.
Remember, all this in front of the z hat, that's SZ, gets plugged into here, right?
I understand that.
Okay.
Yeah.
Because I was thinking about integrating it before with.
Do you need me writing on the board? Or is it clear now?
No, it's clear.
Okay. Okay.
We're about to mess up.
Okay, before I go to you, was there another question over here? Did you have a question? Or... Then I'll come back to you, okay? Okay, go ahead. Okay. Tell me where.
That formula, the rho of H, electromagnetic, how did you get that? 'Cause that's not what it says. Yeah.
This is Ampere's law. That's one of Maxwell's equations, right?
Is that just like a given?
Well, it's one of Maxwell's equations. Yeah. Now, we don't derive Maxwell's equations, right?
Yeah.
They're fundamental physical laws that we believe in, hopefully. They've been experimentally tested and verified. We believe in them, I hope. Yeah. Yeah, so, and of course, Faraday's law, because it has E on the right-hand side, that's, of course, a very good law to use if you already have H and you're trying to solve for E, right? Here, we're doing the opposite, right? That's why we had Faraday's law. Okay, well, I think he was first, though, okay? Oh, okay, that's fine. Okay, yeah, go ahead. For the what question? Yeah, okay. 1 over eta? Well, that's what he was asking. I mean, if the exam doesn't say you have to simplify, I don't think you're gonna lose any points if you don't. Yeah, I think so. If you just left it as omega over mu epsilon 0, yeah, whatever. Yeah, Okay. All right. Yeah, I think so. This exam was not supposed to be, well, I mean, this exam here was not supposed to be really covering plane waves. So I'm not sure if you were supposed to really know about eta 0 or not, but anyway, we know about it now because we talked about plane waves, right?
Originally.
But I wouldn't worry about that. I wouldn't worry about that. Okay, did you have a question? Or yours was answered. Yeah. Okay, that's good. That's good. Okay, so let's move on. Okay. For fall 18?
The last one.
This same problem here?
I was confused about part C.
Okay, this problem here though, right? Yeah. Okay, let me go back. Part C? Yeah. Okay. Better seat. Part C. Find the complex power going through a surface S in the upward sense. The surface S is a square. There's 2 meters by 2 meters. And the face of the square is perpendicular to the vector V, which is given by that. Okay. All righty. So now A is the electric field. Part B we did, it's magnetic field. Now, of course, one of the first things we're going to want to do is take the electric field and magnetic field and construct a Poynting vector, right?
Yeah, I got that.
Oh, okay. Okay. So so there is the Poynting vector. Okay. Now it says that the square is perpendicular to this vector. Okay, so that vector is already perpendicular or normal to the surface, but it's not a unit normal. So, so remember, it's always S dot unit normal n, unit vector n. So, but it's pretty simple to take a vector and convert it into a unit vector, right? Just divide by its magnitude, right? So that's the vector v, and we just divide it by, square root of 1 squared plus 2 squared plus 3 squared, right? So that's square root of 14. So that's the unit normal. Okay. And then we dot that. So we dot the pointing vector with the unit normal right here, and then integrate over the surface S. Okay. Now, in this particular problem, okay, of course, it's not always this way, but in this particular problem, the pointing vector is just a perfectly constant vector. Right?
So how do you do that?
Well, I mean, here's the answer, right? There's no X, Y, or Z, right?
Oh, okay.
So when you integrate over the surface, you can pull out the whole integrand, S dot n, and you just have integral of ds left. So that's just going to give you the area of the surface, right? Which is 4 square meters, right? 2 by 2. So that's where the 4 came from, right? Okay. Now, in a more complicated problem, you might really have to carry out calculus and do an integral, right? Like the one we did over that circular, the coax region, that integral over rho, right? I actually had to do it. But here he's going to be multiplying by the area of 4 square meters. Is that okay?
Yeah.
Okay. All right. Okay. All righty. So moving on. Yeah, please. Sure.
We have to draw another bounce diagram and pose it. Is there using these like an equation, or do we have to draw another bounce diagram?
Well, what do you mean by another one?
Um, Without creating a second bounce diagram.
Well, are you talking about like when we make a snapshot and we have the shifted one? Is that what you're talking about? Okay. Now, okay, first of all, in part B, they're not asking for a snapshot, they're asking for an oscilloscope trace, first of all. Okay.
Yeah,
But in part A, which says construct a bounce diagram, that means just your basic bounce diagram, not 2 of them, right? Just your basic bounce diagram. Okay. So if you want to make a snapshot, that's when you got to take the original bounce diagram and then duplicate it and shift it down, right? Okay. Now we don't even need to do that in this problem. It's not making a snapshot, we're making an oscilloscope trace. Okay. So in the oscilloscope trace, you just make the plot versus time, what the oscilloscope would show for the step function. And then you just subtract from that the shifted response. Okay, there's no need to do a second bounce diagram when you make an oscilloscope trace. That makes sense? Okay, but for part A, it just says construct a bounce diagram. So you expect just 1 bounce diagram, not 2 of them, right? So this is oh yeah, you're right. That is weird. Yeah, that is weird. I mean, say, why did it do that? So let's see. So see, this is what we do when we make a snapshot, right? So this would correspond to making a snapshot if we knew that the width of the pulse was 1.5 nanoseconds. And that's what the width of the pulse is, but we don't need to make 2 bounce diagrams because, it's an oscilloscope trace, right? You don't need to. Yeah, I guess there's no harm in it, but it's kind of silly. We don't need to have 2 of them. Yeah, this is what you would need to do for sure, though, for the snapshot, right? Okay. Yeah, thank you. That okay. Thank you. Okay, moving on. Okay, go ahead. Yeah. Another question? So delay, just like we did here, you mean?
Yes. Graph like first, like from the first bounce diagram. Plot it out, like, I delayed it with now. Get like what I would get from this bounce diagram. Correct.
Well, in the oscilloscope trace, remember you're making vertical lines, so you need these two vertical lines. That's probably why we did it like this. But in my opinion, the easiest way to make the oscilloscope trace is instead of doing two like this with two vertical lines, just use this one here. Make the final oscilloscope trace using only one bounce diagram. That's going to be for the step function. And then just take your final plot and then just shift it and subtract, right? So, I mean, you could do it this way by actually making two of them, the shifted one, and then subtracting what you get from here, this vertical line from this vertical line. But that's not the best way, in my opinion. The best way is just to look at the final answer for the step function and then just duplicate it and shift it and subtract. Yeah. Okay, but I mean, there's nothing wrong with this, but I think it's an unnecessarily complicated way of doing it. But doing this with two of them like this, the second one shifted, that's sort of the way you have to do it for the snapshot. The snapshot, though, is when the line runs horizontally, right? Okay, the snapshot, just imagine like a dashed red line running horizontally. That's what you do for the snapshot. Okay, and the horizontal line intersects both bounce diagrams. And you take this one minus this one, that's for the snapshot. Okay. Now, if you take what you get from this one here, this dashed red line, and the oscilloscope trace, it's vertical, right? Oscilloscope trace, and you take the result and say minus what you get from this oscilloscope trace, that'll be the right answer. Okay, there's nothing wrong, technically speaking, with doing it this way. It's just a little bit more complicated than it needs to be. In my opinion, for the oscilloscope trace, just make a final answer for this one, and don't worry about a second one. Just take your final answer, then just duplicate it and shift it on your paper, right? And then subtract. To me, that's the easiest way. I mean, there's nothing wrong with this, though. I mean, you can do it this way, too, if you want. That make sense? Okay. Are you okay with it now?
Yes.
Okay, okay. All right. Okay. Alrighty, so let's move on.
Could you go through problem 3 on fall 2018?
Okay, sure. This is fall 2018, so this one, right?
Yeah.
Okay. Well, this is the exact same thing as blast from the past 5. That's what we did in class, right? That's blast from the past 5. You want to pull that up again?
Yeah.
So this is blast from the past 5, right? Okay. So there's the answer again. Do I need to go through the whole thing again, or some part of it going to go through again?
Yes.
Pardon?
No, I'm just looking through it.
Okay. Okay. Let me just leave it up here for a little bit. Okay, yeah. Let's see, are you talking about this equation here? Or this one?
That's way to think like value.
This one here?
Yeah.
Okay, see now, well, first of all, in this equation here, you can have any odd multiple of pi that you want. Okay. Now, I may have mentioned this when I was doing it, I don't remember, but I went ahead and somewhat arbitrarily picked, minus pi. Now, if you pick any other value, instead of picking negative pi, you pick plus pi, you pick negative 3 pi, plus 7 pi. All you're doing to the right-hand side is adding some multiple of 2 pi. Right? Now, that means your final phase angle, phi, for the reflection coefficient, is going to be different by some multiple of 2 pi. Now, that does not change the complex number, right? So so it's the same gamma L, right? So it just totally doesn't change. Right? So instead of saying e to the minus j pi over 2, it could be e to the minus j pi over 2 times e to the j 2 pi. That just simply doesn't affect anything. Right? When you go all the way around the complex plane, angle changes by 2 pi, it's the same complex number, right? So gamma L is the same complex number. And of course, since gamma L is the same complex number, of course, it's not going to change the L, right? Of course. Right. Right.
Dr. Jackson, how is the standing wave ratio determined in this problem?
Well, it comes from the Vmax and the Vmin, which is given, if I remember right.
Yeah.
So voltage maximum 4 and minimum of 2. So that's, of course, what SWR means, right? Vmax over Vmin, right? So 4 over 2, right? And that's right here. And of course, that was very important because that was used to get the magnitude of gamma L. This was used to get the phase of gamma L, right? And then, of course, once you have the magnitude and phase, you have the whole complex number, right? So here's the whole complex gamma L, which if you like, you can also write it like that. But anyway, there's the whole complex gamma L. Is that okay? Okay, good. All right. Are we okay with this glass now? Okay. If you don't mind, even though it's a review session, if you don't mind, go ahead and get this going around. Okay. Yeah. Okay, ready to move on? Yeah.
Well, the test covered twin beams and microstrip lines, because I noticed that the formulas for them aren't on the formal sheet. So,
Yeah, that's a good question. So, yeah, I mean, if you recall, there were some homework problems related to the microstrip line, right? And for example, involving the Z0 and the epsilon R effective, right? So let me think for a second. Here's my answer. If that kind of a problem appeared on the exam, I'm almost sure you would be given those formulas. Yeah. Now you would have to know how to use them. That'd be up to you. But the exam would give you those formulas. Yeah. Okay, let's move on. Okay, or else you'll force me to go to note 17. Yeah. Paul, which? Okay. So is it this one here?
yeah.
Okay.
Um, it said that A is equal to half. I'm wondering how we got that. I don't know.
Well, the A coefficient is that number that comes from the voltage divider. So that would come from the 50 ohm Thevenin and the 50 ohm on the first line. Now remember, when the pulse first gets launched, it doesn't yet see this whole part of the system yet, right? So when the pulse first gets launched, you only care about the 50 ohm Thevenin and this 50 right here, right? So that voltage divider gives a half, right? Okay.
I had a question on question 3, fall 2021. More specifically on how to come up with the actual snapshot of the like of your wave from the bounce diagram.
So in other words, part B?
Yeah.
Okay. So you're okay with the bounce diagram in part A? Okay. And let's see, so the pulse has a width of 6 nanoseconds. Okay. All right, so this is from part A, the original bounce diagram, which applies for the step function. Okay. Now, since the pulse has a width of 6 nanoseconds, that's how we shift the second one down, right? Now that's what the blue line is. The blue dashed line, here's 4 nanoseconds, here's 8 nanoseconds. So halfway in between, right here is supposed to be 6 nanoseconds on this time scale here, right? So that's the start of the second bounce diagram. But okay, but then, okay, so the pulse though, let me verify it. Let's see. Okay, pulse is 6 nanoseconds and we make the snapshot at 7 nanoseconds. So that's the red dash line. That's where the time we're observing, 7 nanoseconds. So the blue is 6, and then this is 8. So it's supposed to be halfway in between. So the red line is halfway between this point and this point. Okay, right there. And so that means that on the first bounce diagram, this intersection point right here is going to be 1/4 across the diagram. So 1/4 down the line. Okay. But then when you come over to where it intersects on this bounce diagram, this intersection point right here is 1/4 of the way down the line. Okay. So actually it's on both of them 1/4 of the way down. Okay. So it looks like it's jumping, the snapshot is jumping from both bounce diagrams, it's jumping 1/4 of the way down. Okay. So this one is jumping here from 1.8 to 4.8. I'm sorry, let's see. Sorry, this ring, the purple region is 3. So it's jumping from 3 to 4.8. And then this one is jumping from 3 to 0. So one jumps from 3 to 4.8. And the other one jumps from 3, the dashed one jumps from 3 to 0. Okay. It's kind of hard to read, but you see you have the black solid and the black dashed.
Yeah.
Okay, so this is coming from the first bounce diagram, the solid, the dashed one is from the second one. Okay, you okay with that? Okay, now then we subtract, right? So now it doesn't always happen this way, of course, but just by coincidence, the red line intersects this one 1/4 of the way down, and also this one 1/4 of the way down. So that means 1/4 of the way down, that's where they're both jumping. The solid and the dashed are both jumping at the same point. That's not always going to be the case, right? Okay, but they are in this case. So for both of them, they're both 3 until you get to the 4th of the way down the line. So you're just subtracting 3 minus 3, which is of course 0, right? And then once you get past 4th of the way down, the solid is 4.8, the dash is 0, so it's 4.8 minus 0. So it's going to stay at 4.8, right? So it's going to be jumping from 0 to 4.8, and it jumps right 4th of the way down. Okay. Okay, does everything make sense on that? Okay, okay. Okay, ready to move on? I'll give you another couple of minutes to think. Okay, anything else? Okay, yeah. Okay, now the first bounce diagram here, okay, that is what has been plotted as the solid black line, okay? No, the solid black line. The solid black line is from this one, the black dashed line is from this one, and then we subtract. So solid minus dashed, right? That should be the red. Okay, so now are you asking how I got the black one? Well, okay, so remember the purple numbers are the running tally. The purple numbers are the voltage in these triangle shaped regions, right? Okay, so if you look at this red line, I'm right here at this point right here, it's a fourth of the way down. I'm crossing from this triangle region here to this triangle region, right? So 3 is this triangle region, 4.8 is this triangle region. Well, so remember, this is distance running this way. This is time running this way. So this is the beginning of the line. This is the end of the line, right? So this, for example, is halfway down the line. So right here, that is 1/4 of the way down the line. In other words, 0.25 L. Right? Do you agree? Well, I'm looking at, okay, so remember, to get the snapshot, I'm plotting at a fixed time, which is 7 nanoseconds. So that's the dashed red line. Okay, so, and I got to take what I get from this and subtract from it what I get from this. That's the basic method, right? Okay, so let's just focus on what I get from this one. And that's going to be the solid black line. So just ignore this one. So I'm just looking at this dashed red line. Okay, and as I go along this line, which means I'm going from the start to the end of the line, I'm looking at what those purple numbers are. Okay, now everywhere in this triangle, the purple number, the total voltage is 3. So right here on this dashed red line, that's going to be 3. Everywhere in this triangle region, the purple number is 4.8. So right here along this part of the dashed red line is going to be 4.8. It jumps right here, which is 1/4 of the way down. In other words, this distance right here is 1/4 of this total distance here. You agree? Okay. Okay. Anything else? Okay.
Problem 2, fall 2020.
Okay. This one here?
Yes.
Okay. Now, this was the waveform given, so it's not a rectangular pulse. It's like a triangle pulse. Okay. Now, so first of all, let me remind everybody that the bounce diagram is what we use for 2 types of waveforms, the step function or the rectangular pulse, which comes from it, right? By subtracting 2 of them, right? If it's anything other than that, you don't use the bounce diagram, you use this formula. Remember that? Okay, so that's what we're doing here. So we've got the incident wave, the A coefficient, which comes from the voltage divider. And so again, down the line, you see the voltage generator cut down by the A constant, but the voltage generator delayed by distance over speed. CD is the speed of light in the dielectric. C over square root of epsilon R. Okay, but anyway, and so if you're at a certain point on the line, and by the way, we want to be halfway down the line, but anyway, so that's where Z is, like halfway down here. Okay, and so that would be delay in reaching to you, Z over CD. Okay, now let's see. Now they didn't actually give us CD. Okay, but Z over CD, the delay in going halfway down would be, we can figure it out because the transit time T is 4 nanoseconds, and that's the time delay going all the way down to the load, right? So the time delay going down to the halfway point would be what? 2 nanoseconds, right? So if Z is halfway down, Z is equal to L over 2, then that term, Z over CD would be 2 nanoseconds. Okay, in fact, that's why it appears right here, right? 2 nanoseconds. Okay. All right, and here is the initial bounce. So again, just to go over it, you got the same thing, voltage divider, voltage coming out of the generator. Okay, but now it's gone all the way down, hit the load, bounced back, and then reached the halfway point. Okay, so notice that it's in the reflection coefficient off the load here would be what, 25 over 75, so 1/3. Okay, so the gamma L is 1/3 here. Okay, so let's see. It's just kind of a coincidence, but in this problem, the A coefficient is the same thing as the gamma L. They're both 1/3, which is kind of funny, but okay, so it's kind of confusing, but okay. See, there's 2 1/3s here, right? Okay, but anyway, so A is 1/3, but then the gamma L is also 1/3. So that's why there's 2 1/3s here. Okay, but the delay is all the way down, so it's L over CD, and then halfway back, so 0.5 L over CD. All the way down was 4 nanoseconds, halfway back is 2 nanoseconds, so that's why 6 nanoseconds, right? And 1/3 times 1/3, the A and the gamma L is 1/9. Okay, so the first 2 terms here are going to be these right here, and hence we have like this. Now we could keep on going. Let's see, what did it ask for us? Let's see, plot to a time of 10 nanoseconds. Okay. And I think that's probably enough to do that. So the next term would be the one that goes all the way down, goes all the way back, and then goes there. How long would it take that pulse? 4 plus 4 plus 2, which is 10 nanoseconds. So you're not going to see that one until 10 nanoseconds, but it says plot up to 10 nanoseconds, right? So we don't have to worry about that one, right? So what I'm saying is in the series here, all you need to do is keep the first 2 terms. You're not going to see anything from this one right here until 10 nanoseconds. So if you plot up to 10 nanoseconds, you don't care about it, right? So the answer just comes from these 2 right here. And then you're just plotting these 2. So in both cases, the same thing as a plot of the generator voltage, the triangle wave, except all you're doing is multiplying by 1/3 here for the first one, and then 1/9 for the second one. Okay, this one delayed by 2 nanoseconds, this one delayed by 6 nanoseconds. All right, so this one starting at 2 nanoseconds, this one starting at 6 nanoseconds. Okay, now the V0 was 9 volts. Okay, and the A coefficient was 1/3, so it's 3 volts coming out, 3 volts, and delayed by 2 nanoseconds. This one's delayed by 6 nanoseconds, but then it's, remember that the reflection coefficient was 1/3, so it's 1/3. The height here should be 1/3 times the height of this one, 1/3 times 3, which is 1. So this one here is sitting right at 1 nanosecond. Okay, and again, the third pulse would have started right here at 10 nanoseconds, but we don't care about it. We're plotting up to 10 nanoseconds. Okay, is that equation making sense?
Yes. How did you calculate the reflection coefficient again?
Okay, so it's, the formula is RL minus Z0 over RL plus Z0, right? So 50 minus 25 over 50 plus 25, right? So 25 over 75, right? So 1/3. Okay. Now the A coefficient is Z0 over Z0 plus RG. So that's going to be 25 over 25 plus 50, 25 over 75, which is also 1/3. So that's just a coincidence. A coefficient is the same thing as gamma L, that's just a coincidence. Yeah, do you have a question? I'm sorry? Oh, well, okay, go ahead.
Even the 2013 voltage installed is pretty less than that.
It was one of the blasts from the past.
Was it?
Oh, I don't know. Was it? Let's see. What So 2013, you said? Yeah, okay, fall 2013. Let's see, I see,
Spring.
okay, because I was gonna say, I don't see a fall 2013. So you mean spring 2013? Okay. Okay. Is this the right one?
Yes.
Okay. Okay, which, B, okay. Now, let me remind you that this is a Smith chart problem. The Smith chart's not going to be on your exam. Okay. That'll be very important though for exam 2, but that won't be on exam 1. Yeah, I recommend it. But let's save that for the next exam. Good question for that one. Okay. Some more. Some more. On the same problem?
Yeah, sure.
Ah, now A says do not use the Smith chart. Okay. A probe in the line is found that the voltage in the line is a max of 1.5, a minimum 1.5. Okay, so that tells us the SWR is what? 3, right? Okay. A voltage minimum occurs at a distance of 0.75 centimeters from the device. Determine the input impedance of this device. Do the calculation exactly. Do not use a Smith chart. Okay, now this is, the numbers are, I guess, are different, but this is almost exactly the same type of problem that was done in the class notes. You want me to point that out? Okay, so this is the type of problem where you're determining an unknown load impedance. You don't know what the device is at the end. You don't know what the load is. You got to determine it, right? Okay, so let's go back and find that in the class notes here. I believe it's probably notes 11. Let me check. Not this one. Ah, this one. Remember this? So this is exactly the same type of problem, just the numbers are a little bit different. Okay, so here the SWR was given. Now they didn't give us the SWR in that exam problem, but from the data given, we know the SWR is 3, right? Okay, and you got to be given or calculate where a minimum or a maximum is. You can do it either way. Okay, here a minimum was given, so it's 0.092 lambda from the load. Okay, so, and what is the unknown load impedance? Okay, so now here's SWR in terms of gamma L. Here's the turning the formula inside out right here. Here's the magnitude of gamma L in terms of SWR. Okay, it was also in that blast problem. So plugging in 4, although it's 3 in the exam problem, we get the magnitude of gamma L. Okay, and again, we need the phase of the gamma L. Okay, so again, we calculate using the same thing like I did in the blast. The phase. Okay, here we know the Z minimum is minus 0.02 lambda. Okay, we calculate the unknown phase. And again, you could add any multiple of 2 pi to it. It's not going to change anything, but it came out to be a phase of minus 1.99 radians. Okay, so you know the gamma L. And then finally, just like I did in the blast, you plug in here to get the ZL. Okay, so we have the problem here in the notes. And again, it was almost identical to what we did in the blast, right? Almost identical. Okay. So unknown load comes from the unknown gamma L. to get the unknown gamma L, you need to get its magnitude and its phase. It's a complex number. The magnitude of it comes from knowing the SWR, and the phase of the gamma L comes from the information about the Z minimum. Or in a different problem, maybe it would have been Z max that was given. In the notes, we have a formula for where Z min is and also where Z max is, right? So the difference is for Z max, instead of negative pi, this would have been negative 2 pi. Okay, but same kind of approach. And again, any multiple of 2 pi could be added here. Okay. All right. All right, we're getting close to being out of time, but we can probably sneak in another problem here. Anything from the notes that's unclear? Everybody is okay now with the exam procedure. You know the procedure, right? Now, when you come into the exam, please spread yourself out as much as you can. I prefer not to have anybody sitting next to a neighbor. Okay. Sometimes I ask people to move around at random. If I do that, don't be alarmed. I often do that. Okay, but spread yourselves out as much as you can. Okay. Have your ID with you in case I want to look at it. Okay. And remember the note. Please remember the note about the restroom. I don't like to see people leaving and coming back. Okay. So remember that. Okay. Well, thank you very much. See you on Thursday. If you have any questions between now and then, you can email me. And by the way, the grader, the grader is a very nice person. The grader even said, if the students have any questions, feel free to email him, which is unexpected. It's very, very, very nice of him, right? So feel free to email either one of us. Okay. What's that? Uh-huh. Uh-huh. Wait, just one second.